Good morning, FST students. We're going to be moving into a new chapter, chapter 15 in your textbooks, which is titled Combinatorics, which is the theory of counting, and we're going to study several different counting methods, counting the number of ways that things can be done. As a start of that, we're going to talk about something called a Venn diagram, which you've probably studied in some of your other classes here. But looking at the Venn diagram that I have drawn here, you've got a rectangle which includes a universal set. And the universal set is symbolized by U. And then you've got two overlapping sets here of A and B. Those could be anything. A could represent, or the universal set could be the juniors in Springfield High School. Set A could be those that play basketball. Set B could be those that take a chemistry class. And so you might have some students that take one or the other, or both, or neither. Now, if you see in red here, we've got AUB. This U right here stands for union. The union of the two sets. And union is symbolized or means the word or. So if we're in the union of A and B, we're either in A, or we are in B, or we are in both. So in this situation, anything inside these circles would represent the union of A and B. Now below that, we have the upside down U. This is called intersection, and it means and. So if we are in both set A and B, that means they have to be in both of them. The intersection of these would be this inside region where they overlap. That would be the intersection of the two. We can also show the complement. The complement is denoted by a line over the top. So you can see this right here is referred to as not A. That would be anything that is not in the set of A. In this particular situation, that would be everything outside that circle. It would be that particular region, not in A. And then likewise, you can see the last one here is that we're not in the intersection of A and B. The intersection of A and B is denoted here by blue. And so not being in the intersection would be everything on the outside of that and not in the intersection. So we can use that to demonstrate or to show different sets of values. Now, another very important principle we're going to talk about is the inclusion-exclusion principle, which says that the number that are in the union of A and B, the number that are in the union of A and B will always equal the number that are in set A plus the number in set B minus the intersection of A and B. The number that's in the union will equal the number in A plus the number in B, and then minus the number that are in the intersection. All right, so as an example here, just to show this. This example says of the 540 seniors at Central High School, 335 are taking math, 287 are taking science, and 220 are taking both. How many are taking neither math nor science? All right, so using this formula, the inclusion-exclusion principle, the number in the union of math and science should equal the number in math plus the number in science minus the number that's in the intersection of those two. Okay, so in this case, we have 335 people taking math. That would be the number that is in math. We have 287 that are taking science. And we have 287, or we have 220 that are taking both, which is the intersection of the two. Okay, and so therefore, if I add those up and subtract the 220, I should get the number that's in the union of math and science. So showing this, I believe that would come out to be about 402 would be in the union. Showing this in a Venn diagram, this first circle represents M and the second one being science. Obviously there'd be 220 in both. We could represent that in the middle circle there. Now, if there's 335 people taking math class, those 220 are also taking math, so what's left over would be another 115, because together those would have to add up to be 335. And if there's 287 taking science, that means there'd be another 67 in that section right there. The universal set here is 540. And so if I take these away from my total of 540, so if I take 540 minus 330, or minus the 115, minus the 220, and minus the 67, there'd be 138 that are taking neither math nor science. So I've solved this kind of using the inclusion-exclusion principle and then also using a Venn diagram to show this. Now to answer the question, how many are taking neither math nor science? In that case, that would have been the 138. It would also have been the 540, take away the union of the 402. 540 take away 402 would be 138. Here's another example of the 52 teachers that SHS, 27 like to go sailing, 25 said they like to go fishing, and 12 said they don't enjoy either. How many enjoy fishing but not sailing? So I know, if I just put down my inclusion-exclusion principle, I'm going to have the union of fishing and sailing should equal the number that like to fish, plus the number that like to sail, plus the number in the intersection of the two, which means and. Now in this case, I do know that I have 27 that like to sail, I have 25 that like to fish. All right, it said that there's 12 that don't enjoy either one of them. So since there were 52 total teachers, I know 40 must like to either fish or sail or both. That would have to be the union of the two. So therefore, I don't know my intersection, but solving this, 25 and 57 is 52. 52 take away what would give me 40, and that would be 12. Showing this in a Venn diagram, my universal set here is the total number of teachers, which was 52. The union was, or 12 said they don't enjoy either. That would go on the outside here. I have 25 that like to fish, 27 that like to sail. It'd be very difficult to work on this strictly from the Venn diagram, but from what I just found out, I know there must be 12 that like to do both, which means there'd be 13 that just like to fish and not sail, and there would be 15 that like to sail but don't fish. If I add up these four numbers, that should give me the total of 52. These three numbers in the middle should give me my union, which was 40. I hope this helps. I'll give you a short assignment there that's got about 3 Venn diagram problems that I would like you to solve by using the inclusion-exclusion principle and then also the Venn diagram.